Welcome students. Now we will cover electric field intensity due to uniformly charged spherical cell. Suppose it is a conducting cell. Let us remind what are the four steps. Gaussian surface, find out E ds theta, then flux, then we have to find out Gauss law application, then 3-4 combined find electric field. That's our task. Let us start. First, let us draw a sphere. Let this is a sphere. Conducting. That means inside charge is 0. All charges are on the surface. That means my electric field are like this. Now what I have to do? Gaussian surface. How can I draw Gaussian surface? Obviously, very simple thing. Here I will get three cases. On the sphere, outside the sphere, inside the sphere. Let us go for first case 1. Outside. Here we have to think, let this is the center. Better you should use rounder and pencil. This figure is not perfect. I will not award full mark for this types of figure. That's why what I am asking to use rounder. Let us draw. Electric field direction will be this one. Let us take a Gaussian surface. Small elementary. Always remind it for Gaussian surface. This dot mark is the Gaussian surface. And who is this? This is the sphere. Now let this magnitude is ds, and obviously it is normal. This is also electric field. That means E and ds have same direction, 0 degree. Let us apply. Second case is over. Third is flux. So outside means, always remind, Gaussian surface radius is smaller. Original sphere radius is capital R. Outside means R is greater than capital R. Let us move it slowly so that confusion should not be there. Now, flux. What is flux? Surface integral of electric field around closed surface. A dot B. That is nothing but A, B, cos theta. For this case, theta is 0 degree. Cos 0 is 1. E is constant. Moving outside. Now, surface integral. For this case, I took Gaussian surface point, which is from center at a distance of R. So what is its value? Surface area 4 pi r square. So I got flux equal to E into 4 pi r square. Now applying Gauss law, what is flux? Total charge enclosed by the surface, that is the charges on the sphere. So what is it? On the sphere charge is Q. I take it Q by epsilon naught. From equation 1 and 2, what can we write? So I will write from 1 and 2 E into 4 pi r square equal to Q by epsilon naught, or E is equal to Q by 4 pi epsilon naught r square, like kq by r square. So from here, equation 3, we got E is inversely proportional to r square. Let us go for case 2. If I go for case 2, my Gaussian surface is itself the sphere. That means on the surface. If I go for on the surface, small r equal to capital R. Now the previous equation similarly if I will do, I will get E is equal to q by 4 pi epsilon naught r square. And this is for on the surface. And here this is electric field is maximum. Now we'll go for the second case. Third case, inside the sphere. Now let us go for case 3. Case 3 is nothing for inside the sphere. Now look it here. Let us draw the figure. This was my original solid and this is my Gaussian surface. To differentiate you can use double color, but in exam you cannot use double color. That's why it is better to use one is dot dot, one is like this. Inside charge is 0. This was for outside case. Now when I will take for inside, let us take this line. So who is this? This is the Gaussian surface. Now who is this? This is my sphere. Let us draw to the second point, electric field. Here are the charged particles. Electric field is outside. No problem. For this Gaussian surface, area vector is also outside. Electric field is also same direction. Theta is 0. No problem. But here problem is Q is 0. That means if I'll go for same method, since Q is equal to 0, I will get electric field is 0. Same process I have to follow. Like this, I will get an equation. But here since Q is equal to 0, E will be equal to 0. No need to move forward. Now the question is, draw electric field intensity versus R, the graph. Focus to this point. In this case, from inside to surface is 0. We got it here. Electric field is also 0. Let it is my surface. So my point lies here. Then I got on the surface it is maximum. Let it is my maximum electric field. This is for inside. This is my E max. Now what happened? Outside. When it is for outside, I got inversely proportional. This represents inversely proportional graph. This is for outside. Let us repeat what we covered in this case. Check it again. Electric field due to uniformly charged spherical shell outside, on the surface and inside. We followed first Gaussian surface, electric field, area vector, theta, flux formula, then Gauss law, then electric field. Of course, I have to write in vector form, obviously n cap. Then inside it is 0 since charge is 0. for a conducting sphere case. Thank you. Welcome students. Now we will cover electric field intensity due to a non-conducting charge solid sphere. Remind, last class we covered for the solid sphere. Inside charge was 0, so electric field inside was 0. But for outside, it was inversely proportional. On the surface, it was maximum. This is completely equal to same as here. Inside and on the outside the surface and on the surface. Case 1 and case 2 are same. Here case 3 will vary. So I will focus to case 3 only. You will focus case 1 and case 2 like the previous one. What is case 3? This is the sphere. My mistake. This is my, don't focus here, my Gaussian surface. So who is this? This is my original sphere, non-conducting sphere. Who is this? Non-conducting. That means charge is distributed uniformly everywhere inside the sphere. Everywhere it is there. Can I tell total charge? Okay, who is this? I did not mention. This is the blue one is Gaussian surface. First case, what I told, Gaussian surface, then E ds theta. Before that, here I have to do another one, extra thing. What is that thing? The total charge outside, the total inside. I cannot tell in this case, Gaussian case surface, same charge is there. If I write here charge is Q for total, inside I will write Q prime. Let it is the center. Who is this? The radius of Gaussian surface. Who is this? The radius of original surface. Now, case 3 I want to tell you. What is that? Inside the sphere. For inside, that means my Gaussian surface radius is less than original surface. How to find out? Let its inside volume is V prime, outside volume is V. Here, charge density remains constant. That means total charge or total sphere charge by total volume is equal to Gaussian surface inside charge by Gaussian surface volume. Isn't it? Now, from here, what will be the Q prime? That is Q by V into V prime. That means Q by V. V is what? 4 by 3 pi RQ. Original V means radius is capital R, capital RQ. V prime means this is for V prime Gaussian surface 4 by 3. Always students are confusing and doing mistake in smaller and capital R. That's why focus it. So here 4 by 3 pi, 4 by 3 pi cancel. This is Q. So what I got? Q prime equal to Q times RQ by capital RQ. So here I have to do one extra thing. Now same thing I have to follow like others. Flux, that is surface integral of electric field around closed surface. This is the Gaussian surface. Obviously radially outward. This is my ds vector. And similarly, here is a test charge. Always I have to see electric field on test charge is outward. In this case, this is Q naught. Now what we will see, all the positive charges on this will be outward, that is Q naught. that is, here is the test charge Q naught, my mistake, and here is my electric field. So here angle between, they are in same direction, so theta is 0 degree. First point is over. Second point is, third point is phi. Now what is A dot B formula? E ds cos 0. Cos 0 is 1. So I will get here integration of ds. Surface integral of Gaussian surface. Because this surface I am taking, not the outside. Inside, the Gaussian surface. That is E into 4 pi r square. Students are doing here confusing here. Be careful. This is my equation 2. Now applying Gauss law, flux equal to Q by epsilon. Students are also doing mistakes here. They are forgetting to give here Q naught because inside the Gaussian surface charge is Q prime. So Q prime by epsilon naught. Now from equation 1, Q prime is Q RQ by capital RQ into 1 by epsilon naught. Now from equation 2 and 3, we got here flux equal to, my mistake, E into 4 pi r square is equal to Q times RQ by capital RQ into epsilon naught. Now, if I will solve it properly, I will get E equal to 1 by 4 pi epsilon naught times, check it properly, 4 pi epsilon naught, what I am missing here, Q RQ by, so here R square and Q cancel, no need to write RQ, so it is only R. Anything I missed? 4 pi gone, R gone, so Q bar. Or if I write it properly in vector form, KQR by capital RQ, or I will write it here 1 by 4 pi epsilon naught Q small r by RQ, of course n cap, and here what I got, electric field is directly proportional, in equation 4 I got is directly proportional to R because R is variable. So what will be the graph? If we focus to the graph, if I want to know electric field intensity versus distance graph, let this is mine on the surface. Let this is inside, this is on the surface, and this is for outside. Let us go for inside, directly proportional. So this is straight line. I got maximum electric field here on the surface. This represents what? It is directly proportional. Now inside, what I told like earlier, inside it, just I told inversely proportional. So I will draw the graph. This represents, it is inversely proportional to square of the distance between them. Is it clear? Let me remind it again. Outside and on the surface is similar, only inside is different. Just extra part I have to find out Q prime, because Gaussian surface inside the sphere is Q prime. So according to that, I derived first what is the net charge inside the Gaussian surface, then the rest things. So total 3 Gauss laws we covered. First case, of course in this case also similarly test charge Q naught is there. That's why electric field is outside directions. According to that, similarly Q naught, we got the directions. We got electric field, and electric field is nothing but what we got here, lambda by 2 pi r epsilon naught. In this case similarly test charge Q naught is here. That's why repulsions electric field is according to the force directions. Similarly Everywhere we followed these 4 points. Gaussian surface, find electric field direction by putting the test charge, then surface area or area of, that is area vector, then angle between these two. Next task is your flux, then Gauss law application, find electric field. Similarly, we have also placed here, this is the Gaussian surface, but since it is inside, no need because charge is 0, electric field is 0. Same thing is here. This is the Gauss law applications for sphere and linear charge. Next class we will cover for a charged sheet gas. Thank you.